Okay, we've reached our final topic for the semester, the statistical mechanics of chemical reactions. This is also very likely the most complicated set of calculations that we'll do, and for that reason, we will do a number of example calculations, both here at the end of this lecture, but also in the review lectures that are coming up. Our purpose here is to take everything we've learned about the statistical mechanics of ideal gases and apply it now to chemical reactions between ideal gases. So we're going to do everything with this generic chemical reaction, 4 species altogether, 2 reactants, 2 products. And we're going to use the chemical potential relationships that we saw in the last section in order to derive an expression for the Gibbs free energy change of reaction, the standard expression that we derived using thermodynamics earlier, but now using statistical mechanics, and that will give us basically a definition, a statistical definition of the equilibrium constant. Notice that this free energy expression over here only depends on one thing. It only depends on the equilibrium constant, at least as far as molecular properties are concerned. The only other thing it depends on is the concentration, the Q factor, which depends on the concentrations of all the reactants and product species. But apart from that, the only molecular properties it depends on is the equilibrium constant. And so when we understand the equilibrium constant, we're understanding at a statistical level, at a microscopic molecular level, what drives a chemical reaction. So this is a rather important topic and a very illuminating one. If you think and ruminate on the stuff we'll say here for a little while, you'll come to a much better understanding of why chemical reactions go and what kinds of things drive them and what kinds of things are important and what kinds of things are not important, probably than you had before. And for those of us who are going to be in the chemical sciences down the road in all of our careers, that's a really useful thing. It's really good to understand chemical reactions for a chemist. All right. We now have an expression for chemical potential. And the free energy change, the molar free energy change for a chemical reaction really is just a difference in chemical potentials. It's, I say over here on the right, oops, where am I? Here, that, come on, there we are. That the chemical potential difference is just the difference in chemical potential of products minus the chemical potential of reactants. That's the same thing we said earlier in the thermodynamics section. The chemical potential for the molar free energy for products really is the number of moles of reactant C, of product C, times the chemical potential for C, the same thing for D, minus the same kinds of things for the reactants A and B. And we have expressions for all these chemical potentials now. For C, D, A, and B, whatever those molecules are. As long as they're ideal gas molecules, we have expressions for them, detailed expressions. Here they are. All we have to do is plug those expressions in, do a bunch of algebra. And now there's not a terrible amount of algebra, but a fair amount. And we did it, it's basically the same algebra we went through earlier in thermodynamics. And I won't go through it again here. Here's the final result, that the free energy change for reaction is equal to RT log Q over K. That's exactly what we got in thermodynamics. I haven't changed, that's not different at all. Haven't changed anything from that. Except that now this K isn't just a number that we have to get from experiment or something. It's a quantity, or it's a bunch of stuff all packaged into one bundle. This stuff right here that comes from the molecular properties of the gases, the gas molecules themselves. So let's look at that. It's this equilibrium constant which is the important thing. The rest of it is just the same as in thermo. Useful as that is, the new thing and the important thing and the thing that will lead to new understanding is looking at what's in this definition for the equilibrium constant. So in order to do that, I have this section entitled What is K? And so we'll talk about this definition up here, what that means in this section. First of all, the definition or the expression that we have depends on these quantities, the activities of microstates at standard conditions for each of the species involved, species A, species B, C, and D. Each of them has its own separate activity for microstates. What is that physically? Well, here's the definition of it. The activity for microstates, same as above when we were talking about when we were talking about I2 and other individual gases. It's the product of all the partition functions for the various subsystems, rotations, vibrations, electronic, and then this is really the translational partition function down here. And if we plug in and interpret what this is the standard state concentration, this is Avogadro's number, there's the de Broglie volume that we talked about earlier. If we interpret all of that, then it turns out that this microstate activity is really nothing other. It is exactly the same thing as the partition function for the full molecule, the full molecular partition function for all the substates at once, for translations, rotations, vibrations, and electronic degrees of freedom, when the concentration of the species in question is the standard state concentration, C0. And that means that since the partition function is just the number of microstates in the molecule, then that means this activity is just the number of microstates in the molecule. So the activity for any one species involved in the reaction is the number of all microstates of all types available to molecule I when the concentration is the standard state concentration. Oops, that's okay, there we are. That means that if I raise that activity for molecule C, for product C, to the C power, then I'm multiplying together the partition functions for C copies of molecule C, little c copies of molecule C. And that means that this is the number of microstates available to C molecules of capital C when the concentration is C0. And that means that if I do the same thing for D and then multiply all that together, that's the same thing as the number of microstates available to all the products at once. It's the same as the number of microstates available to C molecules of big C and D molecules of big D all at once. So this is just the number of microstates available to the product molecules, period. And notice, that's the quantity that's up in the numerator of our equilibrium constant. So the top, the numerator here, is just the number of microstates available to the products. If we use the same logic now on A and B, molecules A and molecules B, then what's down in the bottom, what's underneath, under here, is just the number of microstates available to the reactants. And so that whole cluster of things, complicated cluster of things, complicated symbol names and everything, is really something simple in the end. It's the number of microstates available to the products divided by the number of microstates available to the reactants. It's just the ratio of the number of microstates available to the products divided by the number of microstates available to the reactants. And so it's measuring, this ratio, what it's doing is measuring how many microstates you had before reaction to the number of microstates you had after reaction. It's measuring the change in the number of microstates that took place in the course of carrying out the reaction for the molecules themselves. But whenever you're doing a reaction like this, there's also changes in the number of microstates out in the surroundings. So far, we've accounted for the changes in microstates that are happening within the molecules themselves, within the system itself. Now we have to account for the changes in the number of microstates that are available out in the surroundings. And that's what this extra factor, this 0-point energy factor, is doing. I've kind of denigrated that in the past, but it's really doing a very important thing. And we'll see, in fact, it's the dominant term in a lot of cases. It's accounting for changes in the number of microstates out in the surroundings. The second law says that what matters is the number of microstates everywhere, in system and surroundings, not just in the system. So there's got to be something that accounts for the changes in microstates out in the surroundings, and that's what this 0-point energy, or ZPE factor, is doing. Let's see why that's doing that. Well, what it's doing, what this quantity delta E ZPE is doing, is measuring the change in energy that took place during reaction and that energy had to either be absorbed from the surroundings or put out into the surroundings. The surroundings either gained that much energy or it lost that much energy, depending on the sign of delta E here, right? If delta E is negative, then that's energy lost by the system and gained by the surroundings. That's going to raise the number of microstates in the surroundings. Likewise, if delta E is positive, then that's the amount of energy gained by the system at the expense of the surroundings, and therefore represents or keeps track of the number of microstates lost by the surroundings. So you can see just by looking at it how it's related, at least, to the change in the number of microstates in the surroundings. It's useful also to point out that when you take this difference between the 0-point energies, what's changing? What is that change in 0-point energies really accounting for? Well, the atoms in all species combined are the same on both before and after reaction, right? The atoms don't change. They just get rearranged. They just get rebonded. And so the only thing that's changing between the molecules at the beginning and the molecules at the end of the reaction is the bonding. And so this change in energy has to be change in bonding energy. So this delta E ZPE, which sounds kind of artificial and abstract, is really doing something very concrete. It's measuring the change in bond energy as the chemical reaction takes place. And so if the bond energy change is favorable to reaction, that means an exothermic reaction, then the system loses potential energy because the bonds all got stronger and that extra potential energy went out to the surroundings, in which case the surroundings gained microstates, or the system gained potential energy, which means the bonds got weaker overall, which means the surroundings lost microstates. And so this extra ZPE factor, as it's called, is really a bond energy surroundings microstates Boltzmann factor, right? It's e to the minus an energy divided by RT, or e to the minus beta an energy. And so it's a Boltzmann factor. It's accounting for changes in microstates for probabilities that occurred in the surroundings. And so, when all is said and done, when we've accounted for the fact that this is just the ratio of changes in the system before and after, and now this is the ratio of microstates in the surroundings before and after, K itself, the whole thing put together, is just the number of microstates available to the products in both the system and the surroundings at standard state conditions, C0, divided by the number of microstates available to reactants in both system and surroundings at C0, which is a really simple thing. All that K is doing is keeping track of how many microstates there were to start with and how many microstates there were at the end, and taking the ratio of those two things. And that's the thing that controls which way a chemical reaction goes, how far a chemical reaction goes, whether a chemical reaction goes forward or backwards, and whether it goes to completion or whether it stops midway, whether it goes a lot or whether it goes a little. All those things are controlled by this very simple quantity, the ratio of microstates available both before and after. So, to summarize a little bit, a chemical reaction is going forward or going backwards is very much, when it goes forward, when it goes at all, when it's not at equilibrium, it goes because something very much like this process that we talked about very early in the class is taking place. You start with a system that's got a certain number of microstates, you release a constraint, in this case removing a barrier. Now the number of microstates is vastly increased. And because the number of microstates is vastly increased, the probability of seeing these kinds of configurations where everything is spread out is hugely greater than seeing configurations like this where everything is confined, even though there's no reason, there's no physical, there's no mechanical reason anyway why you couldn't see an arrangement like that. It's just that it's extremely improbable compared to arrangements where everything is spread out. It's just statistics that cause, statistics together with randomness, random energy running around, fluctuations if you like, that's causing this overall spontaneous process to occur. And all that's happening in a chemical reaction is instead of just one, big box like this for the molecules, there's also little tiny boxes inside the molecules for rotations, vibrations, and electronic degrees of freedom, which also contribute to the microstates. And there are microstates out in the surroundings, which also contribute to the overall microstates. So as soon as you take into account all of the ways in which the microstates can either increase or decrease, everything is essentially the same as this box-type expansion. When something happens spontaneously, when a chemical reaction happens spontaneously, it's because microstates are increasing. It's because system possibilities are spreading out. Okay, that is my interpretation of the equilibrium constant and therefore of the factors that drive a chemical reaction. It's possible to see qualitatively why a chemical reaction will go or why it won't go and which direction it will tend to go, even without doing calculations. Let's see how that works. Let's see how that's done for a fairly simple reaction, a fairly simple gas phase reaction. The water-forming reaction, 2H2 plus O2 goes to 2H2O, assuming that all these things are gases. The water, for example, we keep in the gas phase somehow, so it's not a liquid. All ideal gases, in fact. And let's just look at all the little features that we now know about that are taking place, all the little microstate changes that are taking place when the reactants, in this case hydrogen and oxygen, rearrange their bonding in order to create water. First of all, there's this ZPE factor that's taking into account the changes in microstates in the surroundings. And for this reaction, this is the dominant factor by far. And that's because it's a very strongly exothermic reaction. The bonds over here on the product side, the 4 OH-HO bonds that form water are much stronger collectively than the bonds that were lost, that had to be broken over on the reactant side. There's a big change in energy, all of that, and it's released by the molecules, and it all has to go out into the surroundings. That raises the microstates of the surroundings by a factor, which is e to the minus delta E ZPE over RT, exactly the factor we have. So that's a very favorable factor, and in fact it's on the order of 10 to the plus 80 for this reaction. It's huge. These ZPE factors are often huge, and very often they're the dominant factors in a chemical reaction, as you can expect, right? The bonding energy changes have to be a big effect on any chemical reaction. Then there are the translations. This is the second biggest contribution. In this particular case, it's not a huge effect because there isn't a very big mole number change, right? What matters for the translations is how many moles of stuff there is on each side. And the reason that matters, we can now see, is because it determines how many translational partition functions will appear on each side, right? If I have a translational partition function for H2, and there's 2 water molecules, and I've got 2 translational partition functions for the H2, and another one for the O2, and then I've got 2 translational partition functions for the H2Os as well, But that means there's more translational microstates on this side than there is on the product side. And you can see that by just counting how many moles, and therefore how many translational partition functions are in the numerator, right? These guys are in the numerator, these are in the top, and these guys are in the denominator, they're underneath when you compute the equilibrium constant. In this case, there's more moles on the reactant side, so this is an unfavorable factor. It's a fairly large unfavorable factor. We know this reaction goes forward anyway, spontaneously, and that means that this bond energy factor has to be bigger than this unfavorable translational microstates factor. Then there's the rotational microstates. It's the same story as with translations, basically. You got two hydrogen molecules, each of them is rotating. Each of them has its own rotational partition function. You've got one oxygen, it has a rotational partition function. You've got two waters on the other side. Each of them has its own rotational partition function. That means there's 3 rotational partition functions on this side, 2 on this side. Probably, I'm not actually sure in this case whether this is an unfavorable or a favorable factor. It's not very large either way. But I marked it here as unfavorable because there's 3 factors on this side and 2 factors on this side. But remember, these are nonlinear water molecules, which means these partition functions are a bit bigger and more complex than these partition functions are. So really, whether this side wins or that side wins isn't so clear to me, but I think it's probably that the reactants win slightly again. It's probably not a very big effect either way, but it's slightly unfavorable, I suspect. Then there's the vibrations. We've already seen the vibrational partition functions are all typically on the order of 1. The vibrational modes are frozen out at room temperature usually. They just don't populate. They don't contribute very many microstates. And there's 3 of them on this side. And there's 6 of them on this side, right? Because there's 3 normal modes for every water molecule, and there's 2 water molecules. So there's actually more vibrational partition functions on the water side than there is on the reactant side. And that means this whole vibrational partition factor should be favorable, but vibrational partition functions are just not very big. So it's going to be favorable, but it's not going to be a big effect. And then finally, the electronic partition functions. 1 for hydrogen, there's 2 of them, but it's 1 squared, so it's still going to be a 1. And then a ground state degeneracy of 3 for oxygen. Oxygen has a triplet state in its ground state, so it's got a ground state W0 of 3. And that means the overall partition function for the electronic states for this reaction is 3 on the reactant side in the denominator. And the ground state is unique and non-degenerate for water, so the overall partition function is just 1 for the numerator in our ratio. And therefore you get a small effect, actually, because of the triplet state for oxygen. You get a small effect, a small change in electronic microstates when the reaction takes place, but it's not a very big effect either. Overall, as I say here, the dominant effect is the large energy loss to surroundings caused by the formation of the 4 OH-HO bonds in the H2O molecules. The translations are unfavorable. The rotations are probably unfavorable. The vibrations in electronics just don't matter. They're just too small to have much effect. And the net result is, yes, an equilibrium constant that's about 10 to the 80th, but almost all of that is due to the bond energy changes. All right, that is the qualitative part of what we want to do. We're going to do something next where we actually do a calculation, but there is an issue that we have to deal with first, and that's the fact that for reasons of simplicity mainly, I chose throughout this section on chemical reactions and the equilibrium constant to use activities that are concentrations, molar concentrations, over a molar standard state concentration. And I've defined all of the other quantities in light of that choice, and that means that what we're calculating is a molar concentration, a Kc equilibrium constant. But for gas phase reactions, it's often the case, not always, but it is often the case that what people use is a Kp equilibrium constant, and those things aren't in general the same thing. It's possible to convert between the two. Here's the conversion down here. And with all these words that I'm skipping here, I talk about what the differences are. So here's the conversion factor between them. If you have a Kc, something that's based on a molar concentration standard state, but you want to have a Kp, something that's based on a 1 atmosphere, let's say, standard pressure standard state, then you can convert between the two with this factor in between the standard state molar concentration, the standard state pressure that you want, RT, and then all raised to a power, and that power is the change in the number of moles on the two sides. So for our water reaction up above, the change in the number of moles was -1, right? We lost a mole in going from reactants to products. In that case, delta N would be -1. In general, for our generic reaction, A plus BB goes to CC plus DD, the delta N is the number of moles on the reactants on the product side minus the number of moles on the reactant side. All right, so using that formula, you can convert between the two, and that means, and that's useful because all the table values that the equilibrium constants that you calculate using table values for delta G0, for example, will give you Kp most of the time, usually, for gas phase reactions. And so if we want to compare our calculations here to our table value equilibrium constants, we probably have to convert between the two. All right, the rest of this is filling in some details about that conversion factor, but let's go straight to this example. Let's actually do a calculation. Well, this is an example for the conversion. I'll leave that for you to look at. One other topic before we get to the example. I'm trying to get down to this example down here, but one other topic before we get there, and that is that it's useful, it's possible and useful to take the equilibrium constant formula that I have derived already up above and factor it out into contributions for translations, rotations, vibrations, and electronic degrees of freedom, just like we were able to do for the partition functions themselves. I mean, the partition functions here, these are all partition functions really, right? They all factor, therefore the equilibrium constant is going to factor too, and that's all I've done here. I've taken all the little equilibrium constants inside these these microstate activities, and factored them all out into their translational, rotational, vibrational, and electronic parts, and then here's, of course, the ZPE factor that accounts for bond energy changes. I'll use these definitions down below so that we get a feeling for how much the translations, the rotations, the vibrations, and the electronic degrees of freedom are contributing to the overall equilibrium constant for a given chemical reaction. We'll do a chemical reaction calculation down below to see that. All right, here's our example finally. Here's the chemical reaction we're going to do our calculation with. I chose this calculation because it doesn't have a very huge change in bond energy. The bonds are pretty strong on this side. In fact, they're stronger on the reactant side in this case than they are on the product side. And so things are, the bond energy contributions won't dominate the equilibrium constant quite so much in this case. It still does, but it's not quite as bad as in the last case. We know that this reaction is unfavorable at room temperature and conditions normally. So we expect an equilibrium constant that's going to be much, much less than 1. We got a big equilibrium constant, or I said anyway that the water-forming reaction has a great big equilibrium constant. Here we're going to see a very small equilibrium constant. And in both cases, the reason is basically that the bond energy was favorable in the previous reaction and is unfavorable in this reaction. All right. We're going to need some data. We're going to need some molecular data to do this calculation. Here's a table with a whole bunch of molecular data. This comes from another textbook, and I'll come back to this table as we need the data. But notice we're going to need vibrational temperatures for each of the reactant and product molecules. We're going to need rotational temperatures for those things too. We're also going to need to know the degeneracies of the electronic ground states, and these obscure symbols, which you probably saw in quantum mechanics last semester, but maybe not. Sometimes they're taught and sometimes they aren't. But they'll tell us the degeneracies. These little numbers up here are the degeneracies of the ground state, so those are the numbers we're actually going to need. The ground state for nitrogen is 1, degeneracy is 1. The ground state for oxygen is a triplet state, remember, is therefore 3, and the ground state degeneracy for NO, nitric oxide, is 2. So those symbols, we don't need the rest of the symbols, we just need those degeneracies. And then we will also need this column over here, which is new. None of the data tables that we've encountered before have this column that's labeled D0. Let me talk about what that D0 is. It's basically it's the negative of the 0 point energy for each of the molecules in question. So this column is going to be used for calculating the 0 point energy. In fact, let me just say something about that. The 0 point energy number that we're going to need to do our calculation is just the minus of the change in the D0 values weighted by stoichiometric coefficients that we get from this column. We'll see more about how that's done as we get down further into the example. All right, let me talk a little bit about what this D0 is. I've been saying all along that if you have more than one molecule, as you do in this case, right? 3 different molecules in this case, then you have to have a common 0 point energy for all 3. The convention is that the common 0 point energy is for all of these molecules to be busted apart. Let me draw that into their atoms, and then the atoms separated to infinity. So a nitrogen atom here and a nitrogen atom way far apart, that's taken to be the 0 of energy for the nitrogen. Take the oxygen, break it apart. So an oxygen atom here, an oxygen atom there, and there's an infinite distance between them. That's the 0 of energy, taken to be the 0 of energy for O2. And likewise for the 2 nitric oxide molecules. All of those also separated to infinity. So all the atoms taken apart and separated to infinity, that's taken to be the 0 of energy. This 0 of energy is used because it's one that's common to all 3 molecules at the same time, right? And it's unambiguous. You take those atoms apart and you separate them to the ends of the earth. That's a clear, identifiable, work-withable 0 of energy, or definition for a 0 of energy. What that means is that if I take any one of these molecules, let's take the nitrogen molecule, and I plot its energy as a function of the distance between the 2 nitrogen atoms, then I'm gonna, if I cram the nitrogen atoms too close together, I start raising the energy. They're too close together at that point. If I start pulling them apart, then the energy starts rising, because now I'm breaking the bond. But right in the middle, where I'm at the equilibrium bond distance, then I'm at the minimum of energy, and that's the 0 of energy for the electronic state, normally. But then remember that there's vibrational microstates on top of those, that electronic energy. And so D0 is the energy up from the first vibrational ground state to the 0 of energy that's common to all 3 chemical species, or all chemical species, no matter how many there are in a chemical reaction. And that's, of course, the negative of the energy down if you were taking this to be the 0 of energy up here where the molecules are separated to infinity. So, taking the differences between the D0 values for all the different molecules will give you the very same thing that you would get if you had some other definition of ZPE and took the differences between all the molecules for that. All right, so this extra column is going to be important, and it's going to allow us to calculate basically the changes in bonding energy between the two sides of the reaction. Okay, so now I'm going to do this calculation, and I'm going to do it one factor at a time. So I'm going to calculate first, let me get rid of all this junk. First, I'm going to calculate the translational contribution to the equilibrium constant, and to do that, I just need the ratio to the appropriate powers of each of these standard translational partition functions. Then I'm going to do the same thing for rotations, then the same thing for vibrations and electronics, and finally this zero-point energy factor. Translations first. The translations can be, so I've used a formula here that I skipped over when I was talking above. Let me just take that as a given. That is the translational contribution. I calculated that formula because it makes the calculation really easy. All you got to do is plug some numbers in. So just take that as a given. It's derived above, and sorry I forgot to talk about that as we were going along earlier. But if you take that as a given and we plug the numbers in, then all you need are the molecular weights for each of the species involved. This number, 0.46009, which you recognize as being from the translational partition function. You need to know the number of mole changes in the reaction. What is the number of moles, the mole change in this reaction? Well, there's N2 on the reactant side, O2 on the reactant side. And there's two NOs on the product side, so there's 2 on this side, 2 on this side, and that's a net mole change of 0. So delta N is equal to 0. This whole term doesn't do anything in this case. And it turns out this term isn't very big either, and we'll see why. The molecular weight for NO is 30. The molecular weight for nitrogen is 28. The molecular weight for oxygen is 32. You can see that 30 squared divided by 28 times 32, that's not going to be a very big number, and in fact it turns out to be almost exactly 1. All this is saying is that though translations each of the translational partition functions for the reactants and products has a lot of microstates in it, it sometimes happens, in this case it did happen, that the number of microstates cancel out on the two sides. The translational partition functions just cancel each other on both sides. And that's what's happening here, which means that there's no real advantage in translational microstates between the reactants and the products. When the reactants go and become products, the translational microstates stay essentially the same. This is the ratio of translational microstates before reaction, after reaction to the number of microstates before reaction, and you can see it's 1. The number of microstates hasn't changed. Translational microstates hasn't changed hardly at all. All right. Next, for the rotations, it's going to be the ratio of the product rotational partition functions divided by the reactant rotational partition functions to the appropriate powers. We need the symmetry factors. For NO, that's 1. The two ends are different. For nitrogen, it's 2, and for oxygen, it's 2, since the two ends are the same. We need the rotational temperatures. Those came from the table above. They were a column in the table above. For all 3 molecules, the temperature is 300 degrees, and the rest is arithmetic. And let's just look at the values. For NO, we have about 120 microstates at 300 Kelvin from rotations. For N2, we have about 52, basically because, why is that? Oh, it's because of this 2 here, basically, because of the symmetry factor. And for oxygen, we have about 72. And when we take the ratio of that, so 120 squared over 52 times 72, we get that there's about 4 times as many rotational microstates in the products as there were in the reactants. So this is a weak, favorable factor in the overall equilibrium constant. This is the rotational factor, and this is a weak, favorable overall factor in the equilibrium constant. Notice I didn't say it up above, but let me say it now. That the fact that this KT is 1 means that this doesn't favor or disfavor reactants or products. This is a neutral factor in as far as the reaction going forward or backwards is concerned. This one is weakly favorable. It's only a factor of 4. That's small for these kinds of calculations, for equilibrium constant kinds of things. Now the vibrational factor. Again, it's the vibrational partition functions for NO squared, because there's 2 of them, divided by the vibrational partition functions for nitrogen and oxygen. Here are the vibrational partition functions. It's the same formula as before. I need the vibrational temperatures. Those came from that data table above. There was a column for vibrational temperatures as well. After that, I just have to plug in my 300K and the vibrational temperature and so on. And of course, because all the vibrations in this case are really high energy vibrations, the vibrational temperatures are all in the thousands of degrees. All of these partition functions are essentially 1. And of course, if you take 1 divided by 1, you get 1. So the vibrational factor in the equilibrium constant is, again, just neutral. Finally, the electronic contribution to the equilibrium constant. Again, it's the electronic partition function for NO squared over the 2 for N2 and O2. In this case, the partition functions are just the ground state degeneracies for the molecules in question. For NO, the ground state degeneracy is 2, as we saw from those term symbols above. For N2, it's just 1, and for O2, it's 3 because of the famous triplet ground state of oxygen. Yes, and here are those same symbols. And I'm just showing here that you can pick off the degeneracies from those symbols. So that means that the overall factor for the equilibrium constant is 2 squared on top over 1 times 3. That's 4 divided by 3. That's 1.33. Again, slightly favorable, but very slightly favorable. It's another essentially neutral factor. So we've seen that all of the microstate contributions from the molecules themselves are essentially neutral for translations, rotations, vibrations, and now electronic degrees of freedom. Finally, our ZPE, or bond energy factor, using the D0 values from the table, 2 times the D0 for NO minus D0 for N2 minus D0 for O2, right? The usual formula for calculating reaction differences for any quantity, in this case for D0s. And noticing the minus sign here, because the D0s are, again, the D0s are for going up from the bottom up to the 0, and we want the value from going down from the 0 to the actual energy. Gives you a value of deltaE ZPE of plus, notice, 180.3 kilojoules per mole, which is pretty modest for a chemical reaction, but is the biggest by far factor that we have encountered so far. So if I put that up in the exponential, divide by 2494 for RT here, that gives a factor of 4 times 10 to the minus 32. So yeah, this is where the whole equilibrium constant really shows up. If I put all that together, if I multiply together all those factors that I calculated, basically a 1 for the translational, vibrational, and electronic factors, and only a 4 for the rotational one, I get about 2 times 10 to the minus 31 for the overall equilibrium constant. Is that quantity correct? Can we compare it to anything? Well, in fact, in this case, we can. We could calculate K from the tables in Appendix A, and in fact, I did that earlier. I didn't write it down here because there's a better thing to do, but And you get something like about 3 times 10 to the minus 31. So we're not terribly accurate, but for equilibrium constants, which have huge factors, right? 10 to the minus 31, 10 to the plus 80, a difference of only a factor of about 1.5 between these two. That's a good prediction. That's a good enough prediction to be doing all kinds of practical synthesis and calculations and engineering, chemical engineering and everything else. That's a good calculation. All right, in addition, once we've calculated equilibrium constants, we can also calculate all kinds of other things for reaction, right? We did this earlier with iodine. We calculated all the thermodynamics for iodine. Now we can do it for a whole chemical reaction. The very first thing we can do is calculate a standard deltaG of reaction. Using our standard formula minus RT log, now we have the equilibrium constant, so just plug our K in there. There we did. I plugged in the calculated K here, not the K I got from the thermodynamic tables. RT is 2494 here, and that gives a calculated deltaG of plus, notice, 176.1. Those plus values, both up here for deltaE, and down here for deltaG are telling you that yeah, this is not a product-favored reaction. This is a reactant-favored reaction. This is a reaction that really doesn't want to go forward, really likes its reactants better than it likes its products. Let's check this value. This is a table value. This is something we can get from the tables. Here's the value for deltaG of formation for nitric oxide. And you can see from that value in the table, okay, these are both elements, so they both contribute 0. Gives you 175.2. That compares very well to this 176.1. As with all the other cases where we've compared table values to calculated values, we're doing extremely well. We're getting very close. If you calculate the percent difference here, it's only about 0.51%, less, well, just barely a 0.5% error between these two numbers. So very good. There is a technical issue here, and I discuss it in this little section of the notes. We actually calculated this deltaG assuming, remember, 1 molar standard state and assuming activities that are based on molar concentration. But then we calculated this deltaG from the tables for gases where the standard state is 1 atmosphere and the activity would be based on pressure in atmosphere units. How is it that we're getting good agreement like this when we calculated essentially 2 different physical quantities, right? One based on 1 standard state, one based on a completely different standard state. And the answer is that in this case, remember, delta N, the number of moles on both sides, the change in the number of moles on both sides, is 0, which means that the 2 types of equilibrium constants, Kc and Kp, are the same in this case. Let's go back up and see that. So up here, yeah, here's our formula for converting between Kc, which is what we calculated, and Kp, which is what we get from the tables. It depends on this difference, this change in the number of moles, which is 0 in this case. That means all of this is just a 1, which means the 2 are the same. So for this case, we could get away with calculating deltaG using the molar standard state and then calculating again using the atmosphere standard state and get the same answer either way. But that won't work in general. In general, you would have to convert this number or convert the equilibrium constant, one of the two, from a Kc to a Kp. And this is just showing, this is just showing how to do the conversion if you want to convert the deltaGs themselves rather than convert the equilibrium constants. But you can do it either way. If converting the equilibrium constants is easier for you, do it that way. All right, let's now convert or calculate all the other thermodynamic quantities that we can. We can calculate a delta energy, right? A deltaU, because we know how to calculate U's, and we can do that for all 3 molecules, NO, N2, and O2. weighting things by stoichiometric coefficients as always. And we just use our standard formulas for all three molecules. This is just three calculations of exactly the same sort that we did for I2 up above. And if we do, we get some values: 621 kilojoules per mole for NO, minus 935 kilojoules per mole for N2, minus 487 kilojoules per mole for O2. Notice there is one thing that I should point out here, that in all of, we set these ZPE factors to 0 when we were doing I2 because there was only one molecule. Now there's three different molecules. We can't set those to 0. And so these ZPE factors are all in here. These quantities are D0. This is D0 for O2. This is D0. This is minus D0 actually for N2. And this is minus D0 for NO. And so they're all, and I added a minus D0. That's why there's a minus there. So all these D0 values here were put in because those are the ZPE factors that we have to now keep track of when we have more than one molecule involved. And if you do all that, you find out that all the contributions except the ZPE factors all cancel each other, right? These are all linear diatomic molecules, so they all have the same rotational and translational contributions to the internal energy. And the vibrational contributions are all negligible, totally negligible. So everything cancels except for these ZPE factors. And in fact, that means that the overall energy change in this case is just the same thing as the energy change in the ZPE factor, and that's 180.3 kilojoules per mole. Now for deltaH, we can use deltaH is equal, for an ideal gas, is just the enthalpy is just the energy plus nRT. And that means deltaH for reaction is deltaU for reaction, plus delta N, the change in the number of moles, times RT, but that's 0 in this case, which means that the deltaH is the same as the deltaU, again, for this case. And again, that's 180.3. Now let's calculate deltaH from the tables. DeltaH for reaction is a value that's in the tables. It's 91.3 for a single NO molecule. It's 0 and 0 for the two elements being N2 and O2. And that gives 182.6 kilojoules per mole. There's a small difference between the two, but it's only about 1%. So again, we're doing extremely well comparing experiment and theory. Finally, let's do delta S. We can do delta S because delta G of reaction is delta H of reaction minus T delta S of reaction, right? And that means we can solve for delta S of reaction here. When we do that, we get delta S is equal to delta H of reaction minus delta G of reaction divided by T. We have these two values, so plugging in 180,300 for delta H, 176,100 for delta G, divided by our temperature 300, gives 14 joules per degree Kelvin per mole for our calculated delta S values. Now we can do the same thing, but using the table values for delta S. And if we plug the numbers in from the tables, we get 24, almost 25 joules per K per mole. So for the first time, we're seeing an actual significant difference between what we calculated here and what we got from the tables. And I don't know what the origin of it is in this case. It's a little bit funny, but I suspect that the reason for the big difference in this case is the D0 values that we use to calculate deltaU, and hence deltaH. Those are values that are rather, you're taking a great big difference between big numbers and getting a small result as a small answer as a result. And that means that if there's a small percentage error in the D0 values, it leads to a large percent error in deltaU and deltaH. Those numbers then go into our calculation for delta S. And so I don't know for sure, but I suspect that's the origin of the discrepancy in this case. I don't think it's the calculations themselves. I think it's the actual data values that we put into the calculations probably have enough error in them to cause This is still a fairly small error, but it's now percentage-wise a pretty big error. All right, that is the end for all of this class. This is the last lecture on new material for this class. I will create some new lectures next week, but they will be basically going over homework and test-like problems. We'll basically be practicing all these formulas with a lot more examples over the course of the next week.